2025 A-Level Combined Mathematics Paper 1, Part B, question number 14, Part B. Part A of this same question was discussed in a previous video, link in the top right. Part B of this question usually has to deal with optimization of some geometrical object. Usually we have a three-dimensional object, like for example we have a cone in this case, where we have to maximize or minimize either volume or surface area of that three-dimensional object. In this case it says, a right circular cone is to be inscribed in a sphere of radius 3 cm as shown in the figure. So here we have a sphere of radius 3 cm, and inside of the sphere we have a cone. We have a cone such that the apex of the cone is touching the sphere, and additionally the entire circle of the base of the cone, as in the outermost circle of the base of the cone, is also touching the sphere. Now given this, they say, let h centimeters be the height of the cone and show that the volume of the cone v centimeters cubed is given by v equals pi by 3 times 6h squared minus h cubed. Now here we can see in this formula for the volume there is no radius. Now usually for a cone you would have the volume of the cone being equal to 1/3 pi r squared h. Now in this case we do not have the radius in here, we don't have this base radius, instead we only have the height. So what this means is that somewhere along the way we're going to have to replace the radius with the height. So we're going to have to write the radius in terms of the height in order to get the volume, this volume here, in terms of only the height. So the reason we want to do this is because in the next part of the question they say, also show that the largest such cone that can be inscribed in the sphere is obtained when h equals 4. Now in this case the largest cone, we have to assume that when they say largest cone they mean the cone with the largest volume. Now it's not exactly clear because obviously you could potentially have the largest cone being the cone with the largest surface area, but in this case we want to assume that the largest cone means the cone with the largest volume. Ideally the question should itself say, show that the cone with the largest volume that can be inscribed in the sphere is obtained when h equals 4. So in order to do this, in order to find the optimized value, the largest cone, the largest volume cone, which is the thing we're trying to optimize, the volume that can fit into this sphere, what we're going to have to do is to take the derivative of the volume with respect to a single variable, which in this case is the height. So when we take that derivative of the volume with respect to the height, we then get a certain value, and this formula, when we check when it's equal to 0, we will see that there's a particular value of h at which that derivative is equal to 0. Now the values of h for which the derivative are equal to 0 correspond to either local minima or local maxima in the graph of volume versus height. In this case, we want to find local maximum since we are looking for the largest such height. So, largest such volume rather. So for this reason, we are going to have to find dv by dh, find the values at dv by dh equals 0 and consider which of those is going to be representing a local maximum, and then we're going to have to conclude that that local maximum is corresponding to the largest volume of the cone. So to start this off, I've drawn the diagram in the answer sheet as well like this. I've also marked a couple of the points. You can see this point here, C, is the center of the sphere. This point O is the center of the circle that is the base of the cone. And then additionally, we have this point A at the top, which I guess A for apex because it's the apex of the cone. And we have this point B at the bottom here, which is the point at which, one of the points at which this circle of the base touches the external sphere. So we could say maybe B for base. So you can also see I've additionally marked a couple of lengths. Since the length AC is a radius of the sphere, since the center C is the center of the sphere and the point A is on the surface of the sphere, this length is 3 centimeters. Additionally, if you consider this length CB, the length CB is also a distance from the center of the sphere up to the edge of the sphere, which means this is also 3 centimeters. Now additionally to that, I've also marked this length from O to B as the radius R, and that's going to be the radius of the base of our sphere. So not base of our cone rather. So given this setup, let's just say let A, B, C and O be the points as shown in the diagram. Now the reason I'm doing it like this is because I can't be bothered to individually label each of these. Like if I wanted to, I could say let A be the point at the apex of the cone that's on the surface of the sphere, let B be the point that is one of the points on the base of the cone that is connected to the sphere, let O be the center of the base of the cone, and let C be the center of the entire sphere or something like that. But rather I would much rather just label them all and define them like this. So now we've defined all of our points. Now additionally, as I said when I was describing this diagram, Since C is the center of the sphere and A and B are on the surface of the sphere, CA is equal to 3 centimeters, which is the radius of the sphere, and CB is also equal to 3 centimeters, which is the radius of the sphere. Now additionally, I'm going to say that this length OB, which is the base length or base radius of the cone, is going to be equal to r centimeters. So I'm going to have to define it. So I'm going to say let OB equal r centimeters. Now additionally, I want you to make another observation. I want you to identify the fact that if you consider the angle AOB, that angle is going to be 90 degrees, since this central apex here is vertically above the point O, which is also passing, this line here is also passing through the point C. So due to that, the angle AOB is equal to 90 degrees or pi by 2 radians. In my case, I'm just going to write pi by 2. So given this setup that we have here, we can now try to find the radius r in terms of this height h here, and given that, we can now try to express the volume of the entire cone in terms of only the height h. So to do that, I'll additionally, actually, I've forgotten to label one. I've forgotten to say that O times OA, the length OA is equal to h centimeters. So let me just add that. Now we've labeled all of the stuff that we know, and we've additionally defined one of the extra variables, OB, to be equal to r centimeters. So now given this, if you take a look at what we have, we can see that the total height OA is equal to h centimeters, but the partial height CA is equal to 3 centimeters. Therefore, the additional height here, OC, is going to be equal to h centimeters minus 3 centimeters. So we can see here that therefore OC is equal to OA minus AC, which is equal to h centimeters minus 3 centimeters, which is equal to h minus 3 centimeters. Now, additionally, we can see if you consider the triangle OCB, the triangle OCB is a right angle triangle. Now, in this right angle triangle, as we just found, we know the length OC. Additionally, from the start, we knew the length CB. What we don't know and what we want to replace is the length OB, which is equal to R. So what we're going to do is to consider the triangle, triangle COB, and we can see, since the angle here, the angle COB, since COB is equal to 90 degrees pi by 2 radians, it implies that the Pythagorean theorem should hold for this triangle. Now, considering the Pythagorean theorem, the hypotenuse here is 3 centimeters, this length here is r centimeters, and this length here is h minus 3 centimeters. Therefore, if we go down and write down the Pythagorean theorem, we can see that the hypotenuse squared, which is 3 centimeters squared, must be equal to one of the side lengths squared, which is r centimeters squared, plus the other side length squared, which is equal to h minus 3 centimeters squared. Now, in this thing, if we simplify this down and remove all of the centimeters squared, since each of these terms has a centimeter squared, we're left with, on the left hand side, 3 squared, which is 9, is equal to, on the right side, r squared plus h minus 3 squared, which is going to be h squared minus 6h plus 9. Now, simplifying this down, we can see if we cancel the 9 and the 9 from both sides, we're left with r squared plus h minus 6h plus h squared minus 6h equals 0, which if we simplify down, we get that r squared is equal to 6h minus h squared. We're going to call this equation 1, and now we're going to go back to what we're actually looking for. We're actually looking for the volume V of the cone in centimeters cubed. Now, considering what we have, we know that the volume of a cone V, volume of the cone V is equal to, from the formula, 1/3 pi times the base radius squared times the height. Now in this case, we're going to call this equation 2, and we can see from 1, we actually can substitute the r squared value for a value that's in terms of only h. So using that, if we do 1, 2, we can see that our V gets turned into 1/3 pi, which I'm going to write as pi by 3, times r squared, which is 6 h minus h squared, times h, which is equal to pi by 3, times 6h times h is 6h squared, and then minus h squared times h is minus h cubed. So that's going to be our answer. We can see that's exactly the formula that we have in the question. V equals pi by 3 times 6h squared minus h cubed. So at this point, we're done with the first half of the question. Now what we need to do is do the second half, where we try to optimize this value to maximize the volume V of our cone, and then by doing that, we find the corresponding value of h, for which V is equal to is equal to maximum value. So for that, what we need to do is first find dv by dh. So here we can rewrite v is equal to pi by 3 times 6h squared minus h cubed. So we're going to find dv by dh. So dv by dh, if we take the derivative here, we have a constant multiple of pi by 3 which we're going to have to keep. So pi by 3 multiplied by, and on the inside here, if we take the derivative of this part, 6h squared's derivative is going to be 6 times 2h to the power of 1, which is going to be 12h to the power of 1. And then minus h cube's derivative is going to be minus 3h to the power of 3 minus 1, or h squared. So this right here is going to be the expression for the derivative dv by dh. Now, in order to find the maximum volume of a cone, what we're going to need to do is to consider dv by dh equals 0. Consider dv by dh equals 0. So dv by dh equals 0 occurs when pi by 3 times 12h minus 3h squared is equal to 0. Simplifying down, we get that 12h minus 3h squared equals 0. This gives us two solutions. If we simplify this down, we can see this will simplify down to 4 minus h times h equals 0, implying that h is either equal to 4 or h is equal to 0, because h equals 0 is also a valid solution, since that will also give us a solution where 4 minus h times h equals 0. Now from these two, one is valid and one is invalid. Now if we consider the situation that we have here, our height h needs to be a positive value. It needs to be somewhere in between 0 and the maximum possible height that it can be, which if you look at the diagram, you can see the maximum possible height that the cone can have is going to be this height, because if the cone looks like this, it's going to have the maximum possible height that it can have. The base radius here is going to approach 0, and we can see that's going to happen when the height is equal to double the radius or the diameter, which is equal to 6 centimeters. So from that we can see that our height h can only vary in between 0 centimeters and 6 centimeters. So we can say, since h is limited between 0 centimeters and 6 centimeters, actually I should write as 0 centimeters and 6 centimeters like this, we'll write it like this. Since h is limited in between these two, the only valid value is h equals 4. Since h equals 0 is not valid for this range, or alternatively you could say at h equals 0 the volume that's corresponding to the cone is going to be equal to 0, at which point we can say it's definitely not going to be our maximum point that we're looking for. So we could either use that argument or this argument to disqualify h equals 0. So h equals 4 is the only real solution. But now we need to make sure that h equals 4 is corresponding to a local maximum and not a local minimum. So we can say at this point, since h equals 0 corresponds to dv by dh equals 0, we can say therefore h equals 4 is either a local maximum or local minimum. Now at this point we still don't have enough information to say whether it's a local maximum or local minimum. In order to find that, what we need to do is to consider what happens to the volume as you get heights which are greater than 4 centimeters and heights which are less than 4 centimeters. So if we consider that, if we consider for h which is less than 4 centimeters, and of course h must be also greater than 0 centimeters since h is a positive value. For this thing we have to consider what dv by dh is equal to, and then additionally we also need to consider the value of dv by dh for h's which are greater than 4 centimeters, and of course we know the limit is 6 centimeters, so we're going to say less than h. So less than 6, h less than 6. So for these two ranges we need to figure out what dv by dh is equal to, and if for the values of h which are less than 4 centimeters, dv by dh is positive, it means that our graph is increasing or the volume is increasing. And if for h which are greater than 4 centimeters, dv by dh is negative, it means that our graph is decreasing, which means that if we find those two observations, our volume graph versus like if we take height versus volume, height like this, our graph is going to reach a local maximum at the point h equals 4, which is what we want to happen. So we need to make sure that for h's less than h equals 4, the graph is increasing, meaning that dv by dh is equal to some positive value, and for values of h greater than 4, it is equal to some negative value. So if we consider that, at this point you can actually cheat a little bit. You can say, well, the question is obviously going to give us a case where dv by dh is positive for h is less than 4, so you can directly say that dv by dh is greater than 0, and in the same way for h's which are greater than 4 and less than 6, you can say that dv by dh is negative. Like, you can sort of cheat. You can say, well, obviously they're going to give us a question where this works out, where dv by dh is positive for these values and negative for these values, so therefore I can directly say it. But rather, what I would prefer that you do is to actually check it. Like, if you're in a time crunch and you're in a bit of a hurry, you can actually skip this part and directly write these two without actually solving it. But if you go and actually solve it, you can see 4 values of h which are between 0 and 4. If you just substitute, for example, if we substitute 2 into here, we can see, substituting 2, this part here becomes 12 times 2, which is 24, and this part here becomes 3 times h squared, which is going to be 3 times 4, which is 12. So we get 24 minus 12, which is a positive value of 12, which means that dv by dh is positive for that value of h, which is less than 4, which is equal to 2. Now furthermore, for the other value which is going to be the value of h, which is greater than 4 and less than 6, if we consider, for example, 5 here, substituting 5 in, we get 12 times 5, which is going to be 60, minus 3 times 5 squared, or 3 times 25, which is going to be 75, and we can see 60 minus 75 is going to be negative 15, which is a negative value. So therefore it does work. dv by dh is negative for values of h which are in between 4 and 6, and dv by dh is positive for values of h which are in between 0 and 4. So it does work. But if you are in a bit of a time crunch, you can actually directly write these two, assuming that the question is going to give you them as a already in the setup that you get a local maximum at h equals 4. So we can see from these two conditions that therefore the point at h equals 4 is a local maximum. And since there are no other local maximums in the valid range of h, which are the range from h equals 0 up to h equals 6, we can say that therefore h equals 4 corresponds to the cone with the largest volume. Or we could say the largest cone. Instead of saying the cone with the largest volume, we could say the largest cone as well. So there we go. H equals 4 does in fact correspond to the cone with the largest volume. So that's going to be all for this question. Let's now finally consider the marks awarded for each part of this question. So at the start, when you use Pythagoras' theorem to find r in terms of h, when you do all of this work here and you find r in terms of h like this, you're going to get 5 marks. When you then substitute that value of r into this expression here, in order to finally get the volume v in terms of this thing right here, the expression given in the question, you get another 5 marks. On the next page, when you then do the derivative thing and find the derivative, for finding the derivative at the start here, you get 5 marks. And then, when you consider dv by dh equals 0 and simplify down like this, you get 5 marks for considering dv by dh equals 0 and 5 marks for finding the values of h corresponding to dv by dh equals 0. When you then go down and consider the valid value and identify that the only valid value here is h equals 4, and then when you simplify down and you realize that you need to prove whether this is a local minimum or local maximum, and then you do that and write down finally that h equals 4 corresponds to the cone with the largest volume, you get another 5 marks for that. So this is the distribution of marks for this question. And that is going to be all for this video. So I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching and goodbye.